So if we want to walk through the elements of a tree, here tree stores the address of the root, because this is the only element of which the address is stored by us. And all the other can be accessed through the root, coming through a certain path. All right. So if the tree is not empty, that means that this pointer is not equal to 0. Then there is at least one element in our binary search tree. In this case, we recursively call ourselves to the left child, because the left child of the root is the root of the left subtree. Then we visit the root itself. We, for example, check it or list it or do something with it. So to say, it's now a tree walk. And now we walk through the right subtree's elements. We call ourselves to the right child of the root. And that's it. That's all. So it's really, really not too difficult. All right, and now, so we can define two other very similar methods, the so-called pre-order and post-order tree walks, which just differ in the order of these three lines. If we first visit the root and subsequently visit the elements of the left and the right subtree, then it is called pre-order tree. If we first visit the elements or list the elements of the subtrees and finally visit the root, then it is called a post-order tree. Certainly, we will not get this ascending order of elements. These are good for other things. I don't want to go into those details. All right. So now we can list the elements in a tree. What else can we do? For example, because it's a search tree, certainly we want to search for an element. How can we find an element in a binary search tree? Because the only element whose address we know is the root, we always start from the root. For example, if we want to search for the element 14, which is here, then we start from the root. We know that 14 is less than 28, therefore all the elements, because all the elements that are less than 28 are in its left subtree, 14 has to be here somewhere. So we step down one level to the left child. And now we check the root of this left subtree. 14 is greater than 12, therefore we know that 14 has to be here somewhere. And then we check 21, if 14 is less than, and then we check 14, and there it is, we have found it. Certainly if we are looking for an element which is not stored in the binary search tree, then it will turn out through, I will show you, 45 is to be found, it is greater than 28, it is greater than 30, but it is less than 49 and no one is here. So that means that 45 is not stored in this binary search tree. Just note that we just moved in one direction, namely downwards in the binary search tree, so that means that the number of steps to be done is not more than the whole depth of the tree. That will be a good idea for finding the time complexity of